building upon generations of work in astronomy and lots of new evidence, came up with a very simple idea about the universe. And the idea was the universe is expanding. But when you start thinking about that idea, it is really mind-boggling. For example, what it means is that everything in the universe, every galaxy, every star, every planet, every atom in your body was squashed into a tiny space, probably smaller than an atom, certainly smaller than the smallest dot you could make on a piece of paper. Now, that was an idea so strange that even many scientists in Hubble's time struggled with it. But some scientists thought the evidence was so compelling that they started looking at this very carefully and slowly, using logic and the evidence available and sometimes new evidence, they began to figure out what might have happened in such a universe. Hubble had already figured out that if you could calculate the speed at which the universe was expanding, you could calculate when it was formed. Now, think about it. That's actually quite amazing. It means he was saying you could calculate the universe's birthday. That's fairly amazing. Some scientists then began to think, can we figure out what things might have been like at the Big Bang? And they figured out pretty soon that if you have all the energy and all the mass of the universe in one tiny space, it had to be incredibly hot, billions of degrees hot. It also had to be very dense, and it had to be expanding so fast that it would have been a bit like an explosion. Now, it was this image that encouraged an English astronomer, Fred Hoyle, who was always a skeptic about this theory, to describe this, jokingly, as the Big Bang theory. Well, he was being satirical, but the name has actually stuck. Then some scientists began to try to figure out what matter and energy would be doing under these extreme conditions. They got a lot of help because during World War II, a lot of people worked on atomic weapons, and atomic weapons are all about extreme conditions. Einstein had already shown that under extreme heat and temperature, matter and energy are interchangeable. They change into each other. So this was the first thing they found out. At the very beginning, the universe must have been a sort of blur of energy and matter. They also realized that as the universe expanded, it would have cooled. And they knew that matter and energy behave in different ways at different temperatures and pressures. Slowly they began to figure out the precise temperatures and pressures in the first few moments of the Big Bang. And in this way, they managed to construct a good, logical, evidence-based story of what happened during the Big Bang. We can't explain the exact moment of the Big Bang, what happened before, or why the Big Bang happened. Cosmologists have lots of ideas about this, but frankly, no real evidence. So Big Bang cosmology can't do any better than any traditional origin story in explaining why the Big Bang happened or what happened at the instant of the universe's creation. But from a split second after that, they can tell a very good, evidence-based, logical story. We believe that everything appeared in the Big Bang, including even time and space. And at first, things are happening incredibly quickly. We begin our story, in fact, a billionth of a billionth of a billionth of a billionth of a second after the universe first appears. Everything's off the charts. The universe is gazillions of degrees hot, it's incredibly dense, and it's expanding as fast as you can imagine. But as it expands, it cools. And as it cools, distinct forms of energy begin to appear. Four main forms of energy. We call these the four fundamental forces. The first is gravity. That's the force, remember, that Newton identified. It appears a billionth of a billionth of a billionth of a second after the universe is created. Then electromagnetism appears. That comes with positive and negative charges, and of course it's the force we're all familiar with. It's basically electricity. Then we get the third and fourth forces, the strong and weak nuclear forces. These operate over tiny distances, but they bind the center of nuclei together in atoms. Now, some of this energy congealed to form the first matter. Remember, energy is what makes things happen. Matter is the stuff of the universe, its basic constructional material. The first forms of matter were probably quarks, but quarks instantly combined in triplets to form protons, which have positive charges, electrical charges, and neutrons, which have no charges at all. Protons and neutrons will make up the nuclei of all atoms. Very quickly, electrons also appeared. These are much lighter than protons and neutrons, and they have a negative charge. But despite the fact that protons and electrons have opposite charges, they can't yet combine because there's just too much going on, there's too much energy. So we enter what scientists call a plasma universe. All of this happened in just a second or two. The universe is now a mere 10 billion degrees hot. It's still very dense. It's probably about 100,000 times as dense as a piece of rock. So if I were to grab a piece of the universe the size of this rock, it would probably weigh as much as 25 elephants. The universe we've seen is also a plasma. All the matter is in the form of a plasma. That's to say it's dominated by charged particles, protons and electrons. And because they're charged, it's as if the universe was full of Velcro, and they sort of cling on to photons of light, photons of electromagnetic energy as they try to pass through. So the universe is very different from today's universe. Light cannot move freely through it, and you cannot form atoms, which are the basic building blocks of our universe. Then, about 380,000 years after the Big Bang, the plasma ends. And this is a very important sort of mini threshold in the story for us, for two reasons. First, when the plasma ended, you could form atoms. And secondly, the ending of the plasma provided a powerful new piece of evidence for Big Bang cosmology. Let's look at the first reason why the ending of the plasma is so important for our story, the creation of atoms. About 380,000 years after the Big Bang, the temperature of the universe has dropped to about 3,000 degrees. That's about the temperature at the surface of cooler stars. At that temperature, the charges of protons and electrons are powerful enough to bind them together. So suddenly, instead of a plasma, the universe fills up with electrically neutral atoms, because those two charges cancel each other out in each atom. Now, let's pause for a moment to think about atoms. The first two types of atoms we get are hydrogen and helium atoms. Hydrogen atoms have one positively charged proton at the center and sometimes a neutron. Helium atoms have two positively charged protons at the center and usually two neutrons. And whizzing around the centers in both types of atoms, we have electrons, generally as many electrons as there are protons, which is why the charges cancel out. I'd like to read you a wonderful description of an atom by Nathalie Angier, which will give you some sense of its structure. She writes, "If the nucleus of an atom were a basketball located at the center of Earth, the electrons would be cherry pits whizzing about in the outermost layer of Earth's atmosphere." So that's the sort of image of atoms you should have in mind when you think about them. Now, because atoms are neutral, suddenly photons of light can move freely through the universe. The Velcro's gone. They don't get tangled up with charged particles. And that leads to the second reason why the ending of the plasma is so important for our story. It provided great evidence in support of Big Bang cosmology. Back in the 1940s, some scientists had already figured out that as the universe cooled, there'd be a moment when suddenly all the matter went electrically neutral. And at that point, photons of light would be able to move freely through the universe. And they figured out there'd be a sort of flash of energy. And some even said, why not look for that flash? It'd be powerful support for Big Bang cosmology. But strangely, no one went looking for it. And that's probably a sign that most scientists still regarded the idea kind of skeptically. Then, in the 1960s, two astronomers, Arno Penzias and Robert Wilson, who were trying to build a very sensitive radio receiver, suddenly stumbled upon this flash of energy. They're pointing, wherever they point their radio receiver, suddenly they've got this sort of hiss of energy. It comes from everywhere in the universe, and it's extremely uniform. Now, think about it for a moment. That is very strange. If you point to the universe and you point towards a galaxy, you expect to detect energy. But even empty space, that was really weird. And at first they couldn't understand it. Then they talked around to one or two astronomers, and finally someone said, I think you found the flash of energy that was predicted back in the 1940s. It's a very exciting moment in science. Now, this was extremely powerful evidence in support of Big Bang cosmology, because what it supported was a very strange prediction made back in the 1940s. And no other theory could explain why there should be this energy or where it could come from. And that's the moment at which most astronomers finally decided, yes, Big Bang cosmology is real. It's telling a real story about the real universe. Since then, many other forms of evidence in support of Big Bang cosmology have appeared, but still today, Hubble's evidence and the evidence of the cosmic background radiation are the most powerful single pieces of evidence to support Big Bang cosmology. The story we've just seen is one we're going to see over and over again in the history of science. Someone comes up with a new claim about reality, and it's based on logic and it's based on evidence, but there's not quite enough evidence. So people around them treat it as interesting, but don't take it terribly seriously. And then gradually new evidence appears, and at a certain point suddenly everyone thinks, oh yeah, I think this is the way things really happened. And then their claim becomes a new orthodoxy. We're going to see it over and over again in this course. Now, I'd like you to think about the story we've just been telling. It's actually amazing. We humans, by sharing information over many generations, have slowly constructed a good, powerful, evidence-based story, not about what happened 10 years ago, or 100 years ago, or even 10,000 years ago, but 13.7 billion years ago, at the moment the universe was created. Now, I don't know about you, but I think that is quite mind-blowing. Okay, so let's sum up. The Big Bang created everything around us, all the matter and energy. And so it created the foundations for building further complexity later on. And that's why it counts as the first major threshold in our course. After all, the move from nothing before the Big Bang to something after the Big Bang has to count as an increase in complexity.